Okay, hi everyone. Let's start day 2 of our Isabelle lecture. So last time we talked about basic value commands, and we looked at some very simple proofs that were step by step, and we were just proving some simple facts about manipulating various algebraic expressions, numerical expressions. We had one about case splitting. Today, what we are going to talk about is, let's see, day 2 lecture. Today, what we are going to talk about is how do you define your own definitions? How do you write your own functions, right? Because a lot of time you want to define various things that you want to work with and prove new things about. So let's start a little bit, right? So I'm going to define a subsection here titled definitions. So you can write your own definitions, and the way that definitions are written is as follows. So suppose I want to define a operation called append list, right? All this does is it takes a list and it produces another list. I'm going to explain what the tick A does in a little bit, where append list of some input L is equal to L appended to itself. So I'm still going to defer explaining what that tick A means, but let's just look at an example, right? The way that we should read this definition is that this is a function that takes a list as an input and produces a list as an output. And what this function does is that it takes L and it appends it to itself. So, for instance, if I do, where this at is the list appending operation. So if I do append list of, let's say, 0, 1, 2, I want to go to the output panel, and I want to specify that this is a list of natural numbers, then all append list does is that it just duplicates it and it puts it in, and right, it just appends this list to itself, right? Pretty self-explanatory. And what this tick A from before is doing, it's saying that this list can be of arbitrary type. Call it some type, tick A. But the output list will be a list of that same type, tick A. Right? If I wrote like tick A to tick B, then we're no longer guaranteeing that the output list is the same as the input list. But this tick A is just an arbitrary type, right? For instance, I can take the same thing, and rather than saying that this is the input list is a list of nats, I could do a list of rational numbers, right? And it'll produce a list of rational numbers that's appended to itself, right? I could do a list of reals, and so on and so forth. Right. Okay, so this is pretty straightforward. So then, right, I could write something like, how about append 3 times, and I'll say takes a list of arbitrary type, produces a list of the same arbitrary type, and as you might guess from the name, I want this list to take a list and append it to itself 3 times, right? So maybe this is a good place for you guys to pause and see if you can write that definition. Whenever you're ready, we'll come back. So I'll begin in 3, 2, 1. So as always, right, we have this where block. We should say that we should define what append 3 times does on some input L. Notice that this name after the where keyword has to be the same as the definition that you're writing, is equal to L at L at L, right? Pretty straightforward. You can see before when I made a typo that if I type a lowercase l, it's going to complain because this lowercase l has nothing to do with the input, right? We have to define the function definition in terms of the input or known constants, right? Okay. Cool. And you can probably guess that append 3 times will work exactly as you might expect. Append 3 times, right, gives you 0, 1, 2, 0, 1, 2, 0, 1, 2. Right, fairly straightforward. Okay, sounds good. Now, we have so we can define, these cute little functions. We might want to prove various things about these functions, right? For instance, I can write a lemma about the length of append list, where if I fix a variable L, let's say that L is of type arbitrary tick a list, and I want to show that the length of when I call append list on L is in fact equal to 2 times the length of L. Right. This feels like it should be pretty obvious. And if you see here, first I do try 0, it doesn't really work, right? But it really feels like that this is something that's, that's dead simple. And the reason, right, of what we're missing is of what we need to do to help along the automation is that we want to actually expand this definition of append list, right? Back here we defined append list L as L at L, as L appended to L. So I'd like to see that, right? So the way that you access the definition of this append list function is we type using append list. And as I type that, all of these will show up. The first one is what we want, right? Append list underscore def. So I'll type a note here, right? To access a definition, use d underscore def. Okay, cool. And you'll see here, right, that this is, if you were paying attention from lecture 1, you'll see that this append list has this question mark L that we can actually instantiate, right? This one, we can use the fact that this question mark L is actually this particular blue L that we fixed in this definition, right? This question mark L and this blue L are not the same. They're different colors and, right, they're represented by different characters. This question mark L can be instantiated by anything, right? Like, for instance, I can instantiate it with, like, I can instantiate it with L, and it'll be the same as that L, but I can also instantiate it with some, some random thing like R that we never defined, right? Like this, and it'll just put that in everywhere where there's a question mark L. So I want to instantiate this for L, and this will tell the Isabelle that we can that there is a rule that can allow us to rewrite append list L as L at L. If you further recall from lecture 1, we can then, instead of doing using, I can do unfolding to try to expand this inline. So I'll do unfolding append list L, right? Before it's append list of L, after it's L at L, right? Okay. And actually, unfolding is even more intelligent. We don't even need to instantiate it for it to figure out that the only meaningful instantiation that will let us unfold this definition is by instantiating with L, right? So starting off, it's good, just visually help yourself pattern match it, do the explicit instantiation, right? Practice using all of these things that Isabelle lets you do. But as you go along, right, you can just unfold the definition without an issue. Okay. Cool. Now if I try 0, this proves very easily by simp, right? Okay, wonderful. We have a definition. We've learned to work with this custom definition, right? Okay, alrighties. So here I'm going to pause and ask you guys to maybe pause the video and try to write another lemma for the length of append 3 times, right? You can very well guess what the contents of that lemma might be. So go ahead and take a stab at that, and I will come back and do that as well. Okay, and we're back here. I didn't mean to have this yet. Right, almost the same thing, except the length should be 3 times the length of L, right? And the proof, I simply just directly unfold append 3 times def. Right, tag on underscore def to the name of the function to access its definition. Right, I'll show that one more time. Using is just the definition as an extra fact. Unfolding unfolds the definition inline. be careful to keep white space conventions here, right? And Isabelle automation proves this very easily, once again, by simp. Right. Okay, sounds good. Next, let's maybe try to write a slightly more interesting lemma, or let's try to write a slightly more interesting function, right? Let's say that I want to write a function, so subsection definition, sorry, I mean to write functions, right? Let's say that we wanted something, we wanted a definition that takes a list, L, and returns a list with all numbers in L incremented by 1, right? Take a list, let's say, you know, of nats, right, of natural numbers. And we just want to add 1 to every single list, right? Okay. Functions are a good way to try to write this recursively, right? I'm going to go ahead and call this a function. And I'll show you what I'll show you what I mean by why we might want to write this recursively as a function, and I'll show again how we might alternatively write this as a definition. So if I write this function called list add 1, the syntax is similar to a definition, where I can write that this is a nat list, takes a nat list as an input, returns a nat list as an output, where if list add 1 gets the empty list as the input, then the output should, of course, also just be the empty list. And then you'll see here that it's hinting us that we have missing patterns in our definition. Okay, what we have to do is we have to define, well, what happens if the list is non-empty, right? Well, if the list is non-empty, then by definition, it must have an element. So we have to define what happens when the list is made up of some element. Let's call it the head, the first element of the list, consed with the tail of the list, with the rest of the list, right? So if you sort of remember from what we were doing in the first lecture, this H is a singleton element, this T is a list for the rest of the list, right? If there must at least be one element, so that's what H is, but it might be a list of length 1, in which case T is empty, or it might be a list of more things, and T will have more things, right? Okay. And if you're familiar with functional programming, this will come extremely naturally to you, right? But the point is that, okay, we have to define this recursively in terms of T, so in terms of H and T. So we know that we want to add 1 to all the elements of the list. Right now we have our hands on the first element H, so I'm going to just call it H plus 1. And then we have to tack this on. We have to recurse onto the rest of the list, which is list add 1 of T, right? We're trusting that list add 1 will correctly add 1 to the rest of the tail of this list, right? Yeah, and so this is the recursive case, this is the base case, right? So let's take a look here. If I recall, for instance, list add 1 on the list 1, 2, 3, 4, right? I get the list 2, 3, 4, 5, right? Okay, sounds good. Alternatively, right, you could, if you didn't like the way that we had written this this pound sign, you want to be more explicit, you can also say cons of H and T, right? And this would be the same thing. Right, just another way to define the same function. These are, the same thing. We're just rewriting it. It's just instead of using the syntactic trigger, we're using cons, right? And the reason I'm doing this is because if you'll note here that Isabelle does not let you define the same function name twice. So we have list add 1. We have an alternate way to define list add 1. We should call it list add 1 alt, right? Okay. And I'm going to tag on alt to the definitions, right? Because again, in the definitions, we expect that matches the name of the function that we are trying to define. All right. Okay, sounds good. I should also I should also note that this vertical bar right here is how you define different cases, right? One case of the input is if the list is empty. The second case of the input is if the list is non-empty, right? For more complicated recursive definitions, you can have many more cases. And one of the things that this fun is doing is that it's automatically proving various facts about the function. For instance, that all of the cases that we've defined is exhaustive, and it's proving that the function terminates. Right? It's not guaranteed that a recursive function will terminate. Okay, good. Later on, when you encounter more complicated things, you might consider writing something like function, right? And you can see that you'll be given a list of sub-goals to prove for exactly those things that I had mentioned. But in this case, Isabelle's automation is good enough to take care of them automatically. Okay, good. Now, you'll notice that this list add one definition is recursive, right? That if you tried to write this, let's say for the second one here, if you tried to change this fun to definition, right, it will tell you that we don't expect this second line, right? We shouldn't be expecting a definition to be recursive. So you cannot define recursive definitions. If you want to define something recursive, it should be a function, right? That's the main difference. Okay. If you did want to write this as a definition, there is a function that can do this. You can write as like so: definition list add one non-recursive nat list to a nat list, where list add one non-rec of L. We can use something from function that those of you familiar with functional programming, you'll know as the map function. The map function is something that takes a function as an input and applies it to every single element of a list, right? Well, this is not very illuminating for what map does, but the first input to map, here it is, this is useful. The first input to map is a function, right, that of input type A, output type B, and it applies to a list of type A, and after you map this function on every element of the list, now you end up with a list of type B. Right. In our case, the function that we're working with is the +1 function, right? The way that we represent this function is you can write a lambda function for convenience. So, for instance, I can literally write lambda x dot x plus 1. This defines a function where x is the input and x plus 1 is the output, right? So there's a function that just adds 1. Okay, and then map that onto L, right? And you'll be able to see that if I run list add one non-rec on this, it does exactly the same thing, right? 1, 2, 3, 4, 2, 3, 4, 5. Okay, good. Right, so if you insist on sticking with definitions, right, you'll sort of have to find workarounds for to define things non-recursively. Otherwise, functions just let you define things recursively. Okay, fantastic. So now you might want to say, okay, well, I have this function and I have this definition, and they do the same thing. Can we prove that they do the same thing? So let's see how we might try to do that, right? And this is going to be our introduction to very simple inductive proof. So let's write a lemma, right? For list add one are equivalent to each other, where we are, if we fix some list L of type, some natural list L, we want to show that list add 1, this original list one that we defined, of L is always equal to list add 1 non-rec of L, right? Okay, I'm going to sorry that out for now. Okay, and the way that we're going to want to tackle this proof is via an induction. If you go ahead on this and you just try to run Sledgehammer on this lemma, I'm pretty sure it will not solve it, and that's because list add 1 sort of has like two definitions, right? We want to split on two cases. We want to split on either if your list is empty or if your list is non-empty, right? And list add 1 itself, the function, is defined recursively. And what you can remember is that if you're trying to prove something about a recursive function, you are probably expecting to induct over its elements in some way, right? So the way that we are going to do this, syntactically, we want to induct on L. What happens if L is empty? What happens if L is non-empty, right? This is how we set up that proof. So we say proof. Previously in our proof blocks, we've always typed proof dash, right? This dash really just means that we don't want to do anything. We don't want to set up the proof in any fancy way. To set up an inductive proof, you give it an argument. We want to say that we're going to induct on L. And the minute you type proof induct L in the output panel right here, it will give you a proof outline with cases. So I can click that. It's going to automatically paste that in. And then you can look at each case, right? So there's this first case. The name of the case is nil. And so I'm going to take that sorry down there, right? And the goal of this case is to try to prove that this lemma statement holds when L is empty or nil. And the inductive case of this is trying to prove that if you inductively assume that list add 1 of L is the same as list add 1 non-rec of L, then can you prove that when you have one more element, which is cons of AL, in other words, A pound L, right, that list add 1 on this longer list, on a list that's one longer, is the same, right, for these two list add 1 functions, right? Okay, so that's roughly what that means. So let's try to go through here, right? So if at first I just type try 0, well, nothing really happens, right? And the reason for that is because, well, we really want to expand the definitions, right? So we saw before that list add 1 non-rec is a definition. So if I write list using list add 1 non-rec def underscore def, list add 1, not 1 underscore def, right? This will tell us, this will give us access to the definition of list add 1 non-rec, right? Rather than using, I can instead do unfolding, and it will unfold the right side directly, right? Which is just unfolds it into the map definition. Map was something that Isabelle had defined, so this right side over here is we don't have to do too much to it, right? But the left side, we want to see something even simpler, right? For list add 1, by the way, you can control click functions and definitions in the output, and it'll just take you to the function, right? We want to see that list add 1 of the empty list expands to the empty list, right? It just simplifies to the empty list. So if I try to say using list add 1 def, right? It's actually an undefined fact. The reason for that is that functions the definitions of functions are accessed via the .simps, right? And now you can see, and the reason it's .simps is because there can be multiple ways to simplify this function definition. One way is if the list is empty, this is the case that we want. Versus if the list is non-empty, this is the next case. We're not ready for this one quite yet, right? So I'm going to go ahead and pick out this first case by using parentheses of 1, right? List.end.stems listed 2 bullets, parentheses 1 lets me pick out the first bullet right here. right? And once again, I want to say the list add one of the empty list. Well, okay, can we just directly unfold this into the empty list, right? I just want to see this in line. So yes, we can change the using to an unfolding, and this is what our proof state looks like now, right? Now if I do try 0, this is very easily solved by automation. Okay, fantastic. So here, you can see in the inductive case, I'm going to go ahead and delete this then show, right? If you keep in mind, if you remember, then is a keyword that pulls in the fact immediately before where you typed then. So then is pulling in this fact, but this isn't really. So I want to be more explicit. I want to show you explicitly how you access facts in your inductive hypothesis. So we saw here that this was supposed to be, right, the inductive hypothesis. So if I delete show, right, I can instead write like using cons. Would be exactly equivalent, right? So cons is the name of the case, and it contains every single fact that's available to you in this case, right? A and L are the arguments to this case. Okay, sounds good. So just to make this even more explicit, right? I'm going to say have. Usually, later on when we get to more complicated inductive proofs, I like to split out what the inductive hypothesis is explicitly to help me keep track, right? In this case, our inductive hypothesis is that list add 1 equals list add 1 non-rec of L, right? If I say using cons, well, this is exactly what cons is, right? I'm just almost renaming cons as IH, right? This will prove by auto, right? Okay, fantastic. So this is how you refer to the case name, right? How you use the facts that the automatically generated proof skeleton gives you. So once again, right, I want to unfold list add 1 non-rec def. It will tell us that this gets mapped to A append L, right? Now, if you remember, right, the map function is something that takes this function and applies it to every single element on this list. So a way that we can try to simplify this is we can write that, let's call this RHS for simplifying the right-hand side, right, is that, well, if you apply this map to the first element A, then it's just A plus 1, and then it's appended to and then you have to apply this function to the rest of the list L, right? So it's going to be a map of this with L, right? Basically, I applied it to the first element, and then I shoved it into the rest of the list, right? Okay, this we can see if automation gets is able to get it. And then so after we've written this unfolding of the right-hand side, I can now do unfolding RHS to, right, before and after to have it unfold the simplification that we just wrote, right? And then now we're ready for list add 1 dot simps. So if I say using list add 1 dot simps, right, it's going to list me 2 things. This second one is what I'm interested in now because I can, right, you can see that we're trying to do list add 1 of A appended to L. So I'm going to say of 2, right? And then after you've picked out this, right, remember, there's still these like question mark variables. You can further continue to instantiate variables. So this H is supposed to match with that A. So I'm going to go ahead and say that this is of A to instantiate A. And then the next one is the T. This question mark T should be instantiated with L, right? And we get this. Right, but then, well, if this is using, I kind of just want to take this and directly replace it with that, right? I can write unfolding, right? And this will directly, so before, left-hand side is list add 1 of A pound L. After is A plus 1 pound list add 1 of L, right? Okay, sounds good. And at this point, right, you can now use the inductive hypothesis. The inductive hypothesis tells you that list add 1 L equals list add 1 non-rec of L, right? So if I say using the IH, right, it's now able to tell us that this part right here is in fact this part right there, right? Okay. One thing I'm going to do is actually unfold this definition again, because if you'll see, right, so instead of saying using, if I say unfolding IH, it will turn list add 1 L into list add 1 non-rec of L, and then I really want like this part to look visually the same as that part, so you can actually unfold the definition again. Right? You can unfold the definition again, and now you can visually see that, yes, they look exactly the same, right? And now I can try 0, and this will prove very easily, right? Okay, so in this proof, I went through quite a lot of steps. I actually overcomplicated this quite a bit because I wanted to show each step explicitly, right, what the sort of unfolding and instantiation does, right? Alternatively, if you really wanted to be fancy, you can just say, using the inductive hypothesis, and then unfolding all of the relevant definitions, list add 1.simps. Right, the pattern matching is smart enough to figure out that instantiating it with A and L is the only thing that makes sense for this unfolding. And then also list add 1 non-rec def, right? And this will also prove, but a much simpler proof, right? But behind the scenes, this is, you know, sort of the steps that Isabelle will unfold to get to where we got here. Right? Okay. Sounds good. So the next thing that I want to do is I want to define a very similar function to what we defined before. I'm going to go ahead and call it list add 2. You can guess exactly what it is. It takes a nat list as an input, gives a nat list as an output, and here's a good point to pause and try to write this before I write it, and come back and compare. But list add 2 of the empty list should be the empty list, or list add 2 of a non-empty list made up of a head and the rest of the list T is equal to H plus 2 appended to list add 2 of T, right? You could also have defined this using the map style that we did before with list add 1 non-rec, right? That's also fine too. I'm just defining it with the function because I think it's easier to, personally, for me to understand. We can test the simple value command, right? List add 2 of 1, 2, 3 gives 4, 3, 4, 5, right? Adds 2 to everything. Pretty straightforward. And here is a fun little exercise. So I want to show something about the relationship between list add 2 and list add 1, i.e. list add 2 is list add 1 applied twice, right? So I'm going to want to show, so if I say fix some list L of type nat list, right, I'm going to want to show that list add 2 of L is equal to first add 1 to everything to L, and then do it again, right? On whatever that output was, apply list add 1 again, right? Okay, cool. So one thing that I want to point out is that actually before I type that second list add 1, you'll see here that, well, this isn't true, right? Before, when I didn't have that second list add 1, and Isabelle will tell you so if it can easily find it, right? Here it's saying that auto quick check found a counterexample where if L is the list containing just 0, well, they're different, right? It's giving you a counterexample. So this is a very nice feature of Isabelle for sanity check, right? If you want to manually do it, you can run quick check and nitpick, right? These are two different counterexample search procedures. They'll do various things as you get more familiar with them. You'll get a feel for the differences. But yeah, they will both find you counterexamples for why this is not true, right? So this is just a good sanity check for when you're writing a lemma and you want to make sure that there's no obvious counterexamples that the counterexample generator can find. Okay, wonderful. This is a good point for you guys to pause and try to give this proof a go. And we'll come back and we'll do it together, right? Okay, so hopefully you've tried this. So this proof is going to be very similar to what we had before, right? Now both functions are highly inductive, so yes, we will want to be doing induction on L, right? We can select this proof outline, right? And once again, we get the two cases, right? The first one is nil, when the list itself is empty, right? And I'm going to just want to unfold our function definitions. So unfolding list add 2 dot simps, right? That unfolds the left side. List add 2 dot simp of the empty list is empty. And then unfolding list add 1 dot simps will tell us that the goal is just empty list equals empty list, right? I do want to say a note here. So list add 1 dot simps, the right hand side, when we're doing this on second unfolding here, it's actually unfolding list add 1 dot simps twice, because first it'll turn this list add 1 of the empty list into the empty list, and then it's going to turn list add 1 of the empty list into the empty list. All right. So when you do unfolding, it does it greedily. It'll try to unfold as many times as possible. This is why if you try to unfold something that's recursive, that has itself in its definition, you can run into cases where unfolding doesn't quite terminate. So just be careful. If you were attentive in the first lecture, you'll see I did mess up somewhere in there where I tried to unfold something that had itself in its definition. Right? So don't do that. Okay, so this will prove by blast. Fantastic. Okay, then the next case, right? Clearly, okay, we get the inductive definition that list add 2 of L is list add 1 of list add 1 of L, right? Let's just see what happens if we unfold both definitions. This will tell you, the first unfolding tells you that you can, right, it's exactly how list add 2 is defined, right? Add 2 to the first element A, and then apply the function to the rest of the list L, right? And then once again here, right, it's unfolding list add 1 twice. The first list add 1 is, I do want to write this out visually. The first list add 1 of list add 1 of A appended to L, first of all, turns into list add 1 of. The first unfolding gives you A plus 1 appended to list add 1 of L, right? But then you know, Isabelle is going to try to unfold it greedily, and so it's going to unfold this onto the first element again. So this onto the first element is why it writes it as A plus 1 and then plus 1, just tacks it on, and then there's going to be 2 list add 1s, right? The list add 1L is going to apply to the rest of the list, which is that, right? So that's why in the second unfolding you'll see A plus 1, and then of list add 1L. Right? Note that unfolding doesn't try to simplify. It's not going to try to simplify A plus 1 into A plus 2, right? But at this point, you know, we can call the simplifier and list that. So this part is exactly the same as this part via our inductive hypothesis, and A plus 2 is equals to A plus 1, right? So this proves quite easily by simp, right? Okay, sounds good. A bit of a shorter lecture for day 2. But I think we will stop here, and next time we'll look at more interesting inductive proofs.